fatigue life is almost 10 times better than for soldered joints. And that's one of the reasons why sintering is used nowadays for power electronic modules. Here you can also see that in areas where there is no or less pressure, the material is less dense than in the high pressure zone. Unfortunately, in that case, for instance, we cannot go higher. That was, let's say, an experiment for using new materials, for using printed wiring boards. So that was from a research project. At higher pressures, the printed wiring board would be just deformed so much that all of that will fail. On the other hand, that's the reason why sintering as state-of-the-art is mainly used on DCB substrates, which are much more stable, especially mechanically. So, okay, so that's sintering. Here it is a sinter press. In fact, initially when we had the first projects on sintering, let's say 15 years ago or so, there was lots of investigation. Do we need vacuum, for instance, or shielding gas or so? All of that is no longer possible. That is a sinter press one of my staff constructed. It is built into a testing equipment, but you can also use some hydraulic press in order to give up the pressure. What is important here, you see these holes. In these holes, there are some heater elements. So we have a quite uniform heating. And what is really important is that the plates coming together are really parallel. That's really important, because otherwise a point-wise contact will crush the chip. Okay, that's a sinter press. As long as it is parallel and as long as the temperature is well controlled, it is uncritical. That's a typical process. We have a limited rate of heating. Again, all of the solvents must gas out, for instance. Then we have a certain preheating time. It's possibly some kind of activation. Then we heat faster, keep the pressure. In that example, it was 5 to 10 megapascal, which is normally too low. And then we keep it for a few minutes and cool at a limited rate. And that's a typical profile, but we have seen in many cases when we have organics in a paste, we have a limited slope, holding time, and then going fast into the final process step where the interconnection is accomplished. Okay, that about sintering. Sintering, besides reliability, it has a big advantage that in sintering we have silver. Theoretically, the thermal conductivity of silver is 400 watt per meter Kelvin. On the other hand, solder has roughly 50. So you could say it is maybe not really 8 times better, but maybe 5 to 6 times better when you sinter than when you use soldering. And the second effect of the longer lifetime is also important. Another process which was used both for die attachment and also for surface mount technology is electrically adhesive bonding. So die attachment, of course, also can be done with a glue that is not conductive, because most CMOS most CMOS circuits do not really need a conducting backside because they are lateral devices, not vertical devices. But for at least for vertical devices, for die attachment, we need electrical conductivity. On the other hand, also, the second application of conductive adhesives was some kind of surface mount technology on thick film circuits. That still is a really important technology. And the process is quite simple. What we want to achieve is, for instance, a capacitor or some other device that is glued onto a thick film substrate. Here we see that's aluminum oxide. Here, these white lines are silver palladium. And in between here, we see the adhesive. The adhesive consists of epoxy and roughly 88% of silver flakes. So it's silver flakes or powder, and these are mixed into the epoxy. The epoxy is, you know, maybe from household applications, you have two-component epoxy, you mix, and then you can harden, you wait, or you increase temperature. So my mama was always, she went mad when I went with the glue into her kitchen stove, but it makes it much faster. And in that way, you can have that epoxy silver material, and it is first screen printed. We know that process already. Then we have a pattern of that adhesive on the substrate. And yes, of course, when we want to do it correctly, of course, we only have it here on the pads. Yeah, here we have a device in a cross fashion. So here, that are capacitors. That is probably a MELF diode. And in that way, we put the device on, we place it, and then we just harden it in an oven. And the interconnection is just accomplished. That process is quite, let's say, quick and relatively simple. Of course, you need a screen printer, a screen, you need a pick and place machine, but you can have a quite simple oven, either a batch oven, or you go through your normal SMT belt oven, which has a continuous operation. Here we can see several things. One is the silver flakes. What appears dark is the epoxy. Also, these small noses are more or less a result of the screen printing process. So you could say probably the mesh distance is something like the distance between these noses here. So that process works very well. Another alternative, if we do not go for surface mount devices, but if we want to do die attachment, that's an example here where we did it for large chips. So typically, for instance, here that was a DCB substrate. We can put on either a stencil. In that case, the stencil is not for printing, but the stencil is just to keep the chip in the right place. So it's not tilted or it's not rotated better. And then, for instance, we can make something like an X and put the adhesive on. Also in such adhesive bonding, it is really important that we do not get porosity or such a thing. in the interconnection. Again, too many pores would lead to high thermal resistance, and that again would lead to overheating. That's important because in big chips, we normally have high dissipated power. Yeah, that can be both in processors, like in your PC, and also in power chips. It can be, let's say, in the range of 20 to 100 watt, just heating in that square centimeter. And you must get rid of that heat here. So typical curing conditions, for instance, in that case, is 150 to 180 degrees centigrade. It is cured for 15 to 30 minutes. So you could say normally for the lower temperature, it's a longer time. And for the higher temperature, it's a shorter time. And here, for instance, we have a printing thickness of 40 to 60. Here you can say, as you do not lose material, the printing thickness will also be the final thickness of your bond. While in sintering, it is reduced by a factor of 2. And when you have solder paste, also the thickness is roughly reduced by a factor of 2 compared to the printing thickness. Okay, so that is an example. One of my staff took the images when we had a project on adhesive bonding for high power applications. Okay. What is also important, we took that from a company information. When you put on the adhesive for large chips, it is important to have the proper profile of what you print or what you dispense. The reason is, imagine you would print a ring, yeah, and put the chip on. You could be quite sure you have a pore inside that ring. So in the end, you must be sure that always in the middle you have most of the material, and when you put on the chip, the material is pressed to the outside in a way that no porosity can come into existence. That's a trick, and here we can see it. For instance, we print that way, then we put on the chip, and the material is pressed to that outside, coming out, and finally, the best is when maybe it just goes out just a few micrometers over the size of the chip. Yeah, then it's optimum printing, and that means the proper amount must be brought there, and we must have the proper pressure in the placement of the chip. Again, here is that example from a surface mount device. What is not so beautiful here is that there is no more glue under the chip here. That was a different chip. Here we have a little more under the chip with respect to shear strength and with respect to fatigue behavior. It is better to have a certain amount of adhesive under the device, but that also depends on maybe on the size of the chip, and yes, and in a pick and place machine, you have only a limited possibility to control the pressure you use for putting on the chip. Okay, that's it for these thick film devices. What we can also see here is that multi-layer capacitor. It also has some terminals, and these terminals are also typical the silver palladium material, like we do it frequently on top of the alumina here. Okay, here is just an example of several conductive adhesives. Let's start with the electrically conductive epoxy. The Epotec company is an American company who invented such materials, you could say, or such composite materials of silver and epoxy already in the 1960s. And in fact, there are still many adhesives in the market, which are in the market for 40 years or so. Maybe they have been modified, but it's more or less the same material. So here we can say we have the silver powder, and it has 70 to 80 weight percent of silver flakes in. It can be put on the substrate by screen printing or stencil printing or by dispensing with a needle. And there are several aspects which are important. I mentioned when you do your household gluing with epoxy, you mix it. That you will not do with industrial epoxy. Industrial epoxy is pre-mixed. And in order to keep it, to prevent it from hardening from that second on when you have mixed it, you must do something. And the trick is temperature. Yeah, so you can say in polymers, the speed of a reaction is always when you increase temperature by 10 degrees centigrade, you double the rate, yeah, or you lower the temperature by 10 degrees, you have the rate. And that's going to low temperature, for instance, having a material that is hardened, let's say at 200 degrees centigrade, you go down to minus 40, and then the material is just not reacting. It is the reaction is frozen, you say. That is just a question of kinetics. We all have seen Arrhenius equation, which describes that behavior, which is an exponential behavior. And we need that. And for that, we have a so-called shelf life. So we can keep such an epoxy, for example, for 1 year at minus 40. Of course, storing at such low temperature is not so cheap, but in the end, it's manageable. Then we have the so-called pot life. That is the time how long the material can be at room temperature in the fabrication environment, or even on the screen. So maybe here they say 24 hours to 48 hours. That is quite a long time, but the main reason for that is it is a material which doesn't precisely have that reaction rate dependency on temperature. That is for normal epoxies, but that here is a special snap cure epoxy. It reacts a little different. You could say below a certain temperature, mostly nothing happens, but above a certain temperature, it suddenly starts to react. And the reason is there such snap cure materials often have a hardener that is micro encapsulated. That's a trick in polymer chemistry. You can put a hardener in a micro capsule of a third material, and that catches that hardener and keeps it from reacting. But going above that snap cure temperature, just the shield around the hardener is destroyed or dissolved, and then suddenly the reaction starts. So that's a good trick, but not all adhesives are snap cure. But in the end, we also have seen that what important parameters are for such adhesives. You must be able to dispense them, you must be able to store them for some time. You must be able to keep them on the, for instance, on the printing machine for some time. So it shouldn't harden before you put on your chip, for instance. And then we have the hardening temperature. Here the hardening temperature is 215 seconds. As a rule of thumb, if you would take such a starting value, you could say for a not snap cure, but for a normal epoxy, when you lower the temperature by 10 degrees, you roughly need to double the hardening times. So here again, for snap cure, below a certain temperature, nothing will happen. But for a normal epoxy that is not snap cure, just you have that rule, 10 degree doubles or halves the reaction rate. And for instance, here you see that Epotex 70AE, it is also frozen. It is not a snap cure. And for instance, here you see such conditions, 150 degrees centigrade, 5 minutes, or 80 degrees centigrade, 90 minutes. So these are just examples, but more or less most epoxies are in that range of hardening conditions. Sometimes, for instance, you harden at a lower temperature, and because you have some other material in your system that should not be overheated or which could be destroyed, yeah, and where you wouldn't be able to solder at all due to the high soldering temperature. And in that way, you have the temperature as a new parameter in your fabrication. For sensors, you must be really careful about the temperature you use, because the hardening temperature has a significant effect on the functional stability of the sensor. I will not go into the details, but some of my PhD students did their work on that topic. What the hardening temperature has an influence on sensors, linearity, or especially on the offset. Another material that is also can be used, which has the advantage that you can operate the devices later on up to 250 degrees centigrade, is silver-filled polyimide. So polyimide is much more stable at higher temperatures than epoxy. Normally, you would say the limit for epoxy is 200. On the other hand, the short time limit for polyimide is maybe 300 to 350 degrees centigrade. And that means you can operate polyimide adhesive joints high temperature, 100 degree higher than epoxy joints. And again, we must see that thick film technology can be used as high temperature assembly technology. Then polyimide is often a good choice. And again, here the rest of the conditions are quite similar to the epoxy. Yeah, here that was some data given from maybe also company information. For very short time, they even gave 300 to 400 for thermally conductive epoxy. So for the 400, I doubt. Here for the polyimide, they say 500, but here short time really means only seconds. Yeah. Here for the epoxy, they give 175 as, or even 150 as maximum permanent operating temperature, and for the polyimide 350. For the conductive adhesives, you can have very different glass transition temperatures. In most cases, the glass transition temperature is maybe around 100 degrees centigrade, plus minus, let's say 30 or so. There are also epoxies you need, for instance, for sensors that have a higher glass transition temperature. Typical value is, for instance, 30 to 50 ppm per Kelvin, or 10 to the power of -6 per Kelvin, below the glass transition temperature, and roughly 3 to 4 times higher above glass transition temperature. Epoxy, of course, has a significantly higher CTE, maybe 60 or so if it's not filled with silver. On the other hand, by going beyond glass transition temperature, typically in polymers, the CTE increases by a factor of 3 to 4. In these electrically conductive epoxies, we have heat conductivity, which is given as 2, or here 1.5, or also 1.5. That is for traditional adhesives, which are used, for instance, in thick film technology. Companies have done quite an effort to go to higher values. And also we did some research. Some of my PhD assistants, they worked in that field of adhesive bonding for high power, but there was a great progress on the adhesives, and industry, they developed adhesives where they claimed up to 20. Yeah, so, and in the end, when we glued that and measured the thermal resistance of these assemblies, it was not really much better than with normal traditional adhesives. And the reason is that in these cases, always we have a contribution to thermal resistance by the thickness of the adhesive, and we have a strong contribution of the interfaces. And unfortunately, we cannot do much about the interface thermal resistance, and that's always the limit we have. Yes. There was an institute in Bremen, Fraunhofer Institute, and they found out about that, and they had a very good publication on that, and also that explained why adhesive bonding has its limits, yeah, with respect to thermal conductivity. The material itself you can improve, but then you also lose one advantage, that is such adhesives are more flexible than a solder joint. And when you put in more silver, they are stiffer, and then the advantage of flexibility is lost. So here they give shear strengths of 5 to 10. Normally, you could say shear strengths of roughly 10. It's always sufficient. You almost never have a problem where just the force on a device is so high that it rips off the joint. Yeah, so that's not the problem. The problem is more the temperature cycles, which have typically lead to lower stresses. But you can also find adhesive joints which have a strength of, let's say, 50 or so. Yeah, that depends on many parameters. It's depending on the surfaces. It depends on the thickness of the joint. It depends also on the device. Sometimes it's not the adhesive that fails, but the metal layer on the chip, for instance, peels off. And so in that way, that value is you could say it's sufficient, but the value itself is not so important. Specific resistance is, let's say, maybe 10 times higher than for solder, but it's not really a problem. It's always sufficient. Loss factor for conductive material makes no sense. Another parameter is the ionic impurity. Here they give a maximum of 25 ppm per chlorine. That is important because when you have not just humidity but moisture, then ions can be dissolved and the ions will become conductive, and by conductivity you can have problems, high resistance circuits, like some FETs or so. They can have already problems due to creep currents. And the other aspect is chlorine always promotes corrosion, and corrosion is of course also to be avoided. And the main chemical factor for corrosion is chlorine. We will see that later on, but chlorine is to be avoided strictly. On the other hand, if you have bigger parts of material like molding compound or so, the limits are lower for chlorine, but the amount of adhesive in an assembly is so low, yes, so let's say it's milligrams or so, so it doesn't matter if it's 10 ppm or 25 ppm, it's just low, but it must be limited in order to avoid problems. Here there is, we have these examples, and these were examples from a project where we went in several steps to higher operating temperatures, and that was for automotive electronics. Especially we did that technology development for so-called engine controllers or gearbox controllers in a car. And when they are mounted on a combustion engine, the temperature can be high. And so in the first step of the investigation, we targeted at 150, and that I did when I was still in the Daimler company. My successor, he later on did same work up to 175, and we built these and we put them in temperature cycles. And here, so it's temperature cycles -40 to 150. So that means all of the parts, they are put in a chamber, and in a chamber we have on top, we have a hot compartment and we have a cold compartment on the bottom. The cold one is maybe 40 degrees centigrade minus the top one, for instance, 150. And then the specimens are on a lift and they are elevated, brought down, up and down, and always kept for 15 minutes or 30 minutes. And that is repeated. And typically at that time, our design limit was 3,000 cycles, because we expected in a car also there could be 3,000 cycles. So you can say you have a number of days, and on every day you operate the car twice. And so you have 600, if you would operate it every day, you would have 600 cycles. 600 cycles per year. And in 5 years, it would be 3,000, but you don't operate it every day. Also, you don't always have -40 plus 150. So in the end, in that way, the 3,000 were derived. And what we did is these devices were just sheared off. We have also at the intake here a shear tester. We have the devices, they are sheared, and the shear force is the shear force is recorded. And then, of course, it must be on a statistical basis. For instance, we have 10 or 20 specimens which are same. And then we take the mean value, and then we can record the shear strength as a function of cycles. So here, that's different sizes of the capacitor. 603 at that time was a relatively small capacitor. In the meantime, smallest capacitors we have as a discrete device are roughly a factor 10 smaller. But on the other hand, we also know bigger devices have bigger problems. So it was not necessary to look at the smallest ones. And then we can see how the initial strength is reduced over number of cycles. And in the worst case, maybe it goes down to 60% of the initial strength we have in that attachment. Here we take the relative value, because otherwise we would not be able to put it in one graph. For that reason, I have also given the absolute forces at which it breaks. So you can see 2220. So that is roughly 1 centimeter square or so, the device. And that has a shear force of 200 Newton. That means 20 kilograms. So it's quite strong, you could say. What we also recorded is the resistance. In these cases, yes, for the big ones, we couldn't find a change in strength up to 1000 cycles, and also the resistance, of course, for the bigger ones, it's smaller, but also that didn't change significantly. So you could say, okay, they are stable. From the relative values, you can see it up to 3000 cycles, but in that way, you have a guess what you can expect. Now let's have some other aspects of such adhesives. We already have seen the CTE measurement. In fact, we take a specimen of that, for instance, a small block of that material, and we put it in a thermal expansion tester. That's a so-called TMA, which is a thermal mechanical analyzer. In German, you also say dilatometer to measure thermal expansion. And you see we have a low slope, maybe here up to 50 degrees centigrade in that case, and a high slope above that glass transition. Also, we can say in that material, we do not have such really linear behavior, but more continuous behavior. But in the end, you can determine a glass transition, and you can also say here below it's roughly 50, and above it's 200. And again, that rule, increasing CTE by a factor of 3 to 4 is confirmed here. We did that for quite a number of materials for the CTE, so the low to high temperature range. As we can see, the polymer industry has many possibilities to control that behavior. So you could say by the chemistry of the epoxy, which kind of epoxy it is, you can determine where the glass transition temperature is. And by the amount of filler and also by the grain sizes of the filler, you can determine the properties of at low temperatures and at high temperatures. So the more you fill in, the lower the CTE will be. At the same time, the Young's modulus goes down. for such material, but it goes down, let's say, roughly by a factor of 10 when you go beyond glass transition temperature. Also, we must say, for die attachment materials, the CTE itself is not so relevant. Typically, the Young's modulus is more relevant because it decouples or it removes stress from the chip. Again, here we have seen for the different materials how it behaves over temperature, and here we can see there are materials also which have glass transition temperature, for instance, roughly 120 degrees centigrade, and others have a glass transition temperature only around 50 degrees centigrade. What is also important, I have shown you data where we said shear strength is 10 megapascal. Here for that special adhesive, we also measured it over temperature. And you could say, yes, at 20 degrees centigrade, it is roughly 28 or so megapascal. It goes down when you go to above the glass transition, and then it's only 5 megapascal, but you could say 5 megapascal is still sufficient. So with such strength values, you do not have a problem really. Okay, I dropped the comparison between SMD soldering and conductive adhesive bonding. And now let's go to some other processes. I will go through these a little faster. One important process for die attachment, in former times it was eutectic bonding, but now it is more important for wafer bonding. And what does it mean? When we look at the phase diagram, the binary phase diagram of gold and silicon, what do we see here? So that's joy for every metallurgist. What is it here? What we see here? Yes, it's a eutectic, and that means gold melts at 1063, silicon melts at 1404, and we put it in contact and heat it, let's say without oxidizing the silicon. Then the melting point is only 370 degrees centigrade. And that means we could think about a die attachment process for silicon, because most silicon chips we have, they tolerate temperatures of 400 degrees centigrade for a short time. So it normally will not damage them. Many processes in silicon processing are significantly higher. Of course, for the aluminum metallization, we should not go to higher temperatures for longer times. That would not be good, but yeah, such many chips tolerate that a little above 400 degrees centigrade, if it's only for a few seconds. Because then the time is too short for significant diffusion. And so how can we make a process? I told you, you must avoid oxidation of silicon. Silicon oxide is one of the most stable oxide we have in nature. And so when we have only a few nanometers of silicon oxide on top of the silicon and put gold on, we do not have the system of silicon versus gold, but we have this system of silicon oxide versus gold, and that has no eutectic. And on the other hand, we also need direct contact between silicon and gold in order to have an ohmic contact. Yes, we want to have conductivity. And so how do we do that? So typically the silicon chip is coated with gold, but if you sputter gold onto silicon, what will happen? You put it out of the sputter machine and have a sharp look, and then the gold will roll off. Yes, you have a small sausage then, so it rolls itself because the adhesion is low. Yeah, because gold is a noble metal, silicon is almost it's a between ceramic material and metal somewhere. So it has a quite different type of bonding. It has a covalent bonding, and in that way you need something in between. And when you want to metallize silicon, you typically need a layer which sticks to both sides you would want to put together. And one of the materials is chromium. What is the other material we use as an intermediate layer between silicon and gold, or silicon and silver, or so, or sometimes even silicon and aluminum? What do we use in between? Titanium. So I would say titanium is even more important than chromium, but in that example here, they gave chromium. What is also often used is titanium tungsten alloy, but that we don't want here. But titanium tungsten is very good against diffusion of the parts. But in the end, we want to have diffusion here, so we could also use pure titanium. We have the gold, and then we can have, but it's not really necessary, a gold silicon preform. That's, you could say, like a sheet of solder material we can put in between, and on the bottom we need silver or gold on the substrate. We put that together, we heat it to 430 degrees centigrade under nitrogen. So all of that is not in a big oven, it's just heated on a hot chuck. Chip is put on. We have a so-called scrubbing, that's some movement of the chip. And by that scrubbing, the backside of the silicon, on the backside, the chromium and gold are scrubbed away. And so we have direct metallurgical contact to the silicon. And in that way, we can form a joint which has a very good attachment to the silicon, and it has a very good attachment to the substrate. And in between, we have a layer of gold silicon. The disadvantage when we have such a preform in between is, of course, that it is quite expensive, yeah. Because here, for instance, when we look at the eutectic, it is roughly 6 weight% of silicon. That means 94 weight% of gold. And it is almost as expensive as soldering with gold tin 8020, for instance. So it's mostly gold you use here, and that's one of the disadvantages. And so for that reason, of course, it's tried to avoid that gold silicon preform, especially when you go for wafer bonding. So attaching one MEMS wafer to the other in a conductive fashion. So you want don't want to have a square meter of that gold foil here, because that would be too expensive. Okay. The stresses here are really high because, as we already have seen, what is the basic stress formula? Stress is roughly delta alpha delta T times Young's modulus, effective Young's modulus. That's that formula in the exam or so. You will not use that formula directly, but it's important to understand the problem of stress, because the delta alpha is clear, silicon to substrate. Delta T, here we see we go from 420 degrees centigrade to room temperature. That means 400 degrees centigrade delta T. That's quite a lot, for instance, compared to gluing at 100 degrees centigrade. And the effective Young's modulus is also high here, because for one part we have the silicon. That eutectic is also high Young's modulus, and the substrate isn't a polymer substrate, of course. It's also a ceramic substrate, and so the Young's modulus is really high. Yeah. So that means, for instance, if delta alpha is 2 times 10 to the power of -6 per Kelvin, then let's say the delta T would be, let's say here 2.5, that's easier, 400. And so delta alpha, delta T is 10 to the power of -3. That is a thermal strain. And if we multiply that with Young's modulus of, let's say, 200,000, E is then sigma is so we have that here, 10 to the power of 3 times 10 to the power of -3, then it's 200 megapascal. Is that a lot or not? Just for comparison, before I told you sometimes the shear strength is just 10 megapascal, so that would be 20, factor of 20 above the shear strength. Also 200 megapascal is a value where it really is dangerous for the silicon itself. So here we are really on the danger side. Yeah, but again, that estimation was really a rule of thumb, but it shows us the problem, and it also shows us already what are the main affecting factors for stress. Yeah. Okay, so lead frame, for instance, if it's alloy 42 or Covar, then we can stay below these 2.5 as a delta T. Also, when we use aluminum nitride, it's on the good side. Aluminum oxide is fair. And in that way, it must be thermomechanically adapted, especially if the chip is larger than a few millimeters in diameter or so. So that means, yes, it can lead to very high stress. And that's also one of the reasons why we do not use that process so much. The second reason is lead frames nowadays, we mostly use copper. And for copper, the CTE difference would be really high. Yes, would be a factor of 10 higher. And then 1000 megapascal is, of course, out of range. But for wafer bonding, it's not a problem because the wafers we bond together, they have the same CTE. So the delta alpha is more or less 0. Okay, here is another example. That was eutectic bonding. Eutectic bonding nowadays is mostly for wafer bonding, not so much for chip bonding somewhere, but it can be done. That was something also interesting. When I built up this lecture some time ago, I wanted to have some packaging examples, and that example was from Analog Devices company, and it's a MEMS, and it is an acceleration sensor, and it's a monolithically integrated acceleration sensor having the micromechanical structure and also having a microelectronic structure. So at that time, Analog Devices, I think they were the most advanced company in MEMS. In the meantime, also Bosch and other Sensirion and so are very good. I got that, and it really looked like a plastic device. I gave it to my lab. They wanted to cut it, and here we already had a problem because cutting it in half was really a problem. And when we managed, of course, we saw it's not a plastic package; it's a ceramic package, and so here you see something similar to aluminum oxide, but it's dark. The material here is just for embedding. That has nothing to do with assembly and packaging. And here's a chip. Here you can also see the bonding wire, but was interesting, the die attachment. It really looked like epoxy silver. Here the meniscus was more than for a solder material. And what was really strange was that high thickness of that die attachment. Yeah, so it was much higher than we normally see for gluing. And then we analyzed it, and then we found out that it is not epoxy silver, but it is glass and silver. That gray material here is glass. So the company who did that, they mixed glass powder with silver. And of course, glass is melting at a higher temperature. Typically, for instance, when you have vanadium oxide or a mixture of vanadium oxide and other oxides, also in oxides, you can create something like a eutectic, or you can have quite low melting points. And so for vanadium oxide-based glasses, you have a process temperature of 340 to 400 degrees centigrade. And the silver content, again, here is roughly 80%. You can, again, use a needle dispenser, or you use a stencil print, or in order to deposit that material as a paste. And then the chip is dispensed, and what we must say here, glass and glass silver has a higher CTE, which is significantly higher than for epoxy silver. And in that way, when you have such a material, the effective Young's modulus is at least significantly higher than for gluing. On the other hand, again, we talk here about similar process temperatures like for eutectic bonding, and that again, by that delta T effect, leads to high stress. And how can we reduce shear stress? shear stress no. Shear stress is, of course, shear modulus times shear strain, and the shear strain is just the delta L divided by the height of that. So if you increase the height of a die attachment, you could say you effectively reduce the effective Young's modulus. And in that way, the strain is lower, or the strain difference is lower. And in that way, also stresses are lower when the die attachment is thicker. So again, that is just basic mechanics, because we all know how shear strain is defined. Yeah. And in that way, that explains why that die attachment was so thick. It was necessary to avoid stresses and strains in the chip that are too high. Okay, again, we have here that typical profile, limited rate of heating, then faster heating, keeping it here in that case for 15 minutes in order to let the glass flow. It is wetting the parts, and then we cool down. Again, we see within almost half an hour in order to avoid stresses that are too high. So we have, for die attachment, we have seen soldering, adhesive bonding, we have seen silver sintering, and we have seen eutectic bonding, and also we have seen glass soldering or glass sometimes it's also called glass gluing. Okay, that was die attachment, and now we know how to attach a chip on to a substrate. And when we have done that, of course, the next step is, in most cases, we must make an interconnection. Okay, and that's the next part, interconnection technology. It's not that we never heard about that. Here is an example by Tanaka company. Tanaka is or was a Japanese manufacturer of bonding wires, and that was taken from their information material. I must say it is very impressive with respect to the wire bonds we see here. They are high density, so very close together. They all look same in shape, no irregularities, but the rest is not so good. Here we see 3 significant mistakes you can make in packaging. They have nothing to do with the wire bonding, but three things are critical here. It's not so easy to see, but maybe you see it. What is not good here? Yeah, it even gives a shadow in the stem. Yeah, that's not good. Also, the sawing. Yes, evidently, I don't know what happened. They were not sawing through. That's also not good. Yeah. When you saw straight through. And the third thing is, look at the metallization and passivation system. Here you see a crack. Also, that's nothing which should be shown. Yeah. And another thing is, in the in the adhesive bonding, here is too much of adhesive, while it's missing here. So you could see, maybe if they would have attended my lecture before, they would have seen that you can do better with deposition of adhesive before gluing. Okay, so just interesting, but the wire bonding is good, and it must be good. And the next is, I want to explain it. Here is a graph I took from literature, but you can also compute that really easily, because it's just by combining mathematics. And now the question is, when you do wire bonding and you do, for instance, 1 million bonds, how many are not okay, yes, of these? And then you get a defect rate. You can say parts per million, or normally we say here DPM, which means defects per million. And so let's say 10,000 DPM. That doesn't sound so bad, yes, because that's, you do 100 wire bonds and one is not okay. So doing that in the lab for your master thesis, I would say you're not so bad, yeah. But now with such a yield, yes, here 10,000 DPM is a yield per bond of 99%. Yeah, you must keep that in mind. Here that would be a yield of 99.9%. Yeah. If you look at individual bonds, but now you must think about, we sometimes have packages, or we have, for instance, thick film circuits which have 1,000 wire bonds, and all of the wire bonds must be okay. Or if only one wire bond is not okay, all of your circuit is not working. Yeah. So that means in that case, when you have many wire bonds on your module or on your device, you can compute what is the yield, for instance, as a function of the yield on the module level, as a function of the yield on the bond level, yeah, and of course as a function of the numbers of bonds you need together to operate together. And so we can say, for instance, if you have 100 wire bonds, which you have on almost every IC, and you have a yield of, what is it here, 99.5% or so for bonding, then the yield of devices you get is below 50%. So, and that's the worst case. You cannot be worse in bonding. Now let's say when you have a yield of 99.9%, then you can have a module yield of 92% if you have 1,000. If you have 100 wire bonds. Now let's talk about, let's say something realistic, like in a BGA, 1,000 wire bonds. And you have a defect rate of, let's say, what is it, 70 or so. Then again, then you only have a module yield of 95%. But on the other hand, if you have a chip with 1000 IOs, I would say that's not the cheapest one. Yeah, that's quite a lot. If it's an older Intel chip, maybe it's 10 euro, yeah, or a few euro. If it's a new latest type, it can be 100 or so, yeah, euro. And if one bond goes wrong, you throw away all of it, yeah. That's a problem, and that's why it's so important that in wire bonding the yield is high, and that's the reason why there is still ongoing research on wire bonding, and there's more still development. In fact, I just supervise a master thesis on wire bonding in Bosch company presently. Just the process is very old, yes, over 60 years, but in the end, it is not completely managed, and there must be continuous work in order to keep it under control at a level of a few dPm. Yeah, that's the point. You could say you can compute it that way. The yield for the modules is 1 minus the defect rate for one individual bond to the power of n, and n is the numbers of bonds you need operating simultaneously, or the number of bonds you have on that device. And that means even if that x, that's a defective fraction, is almost 1, but if the number n is high, then the whole yield goes down just. So that's a simple combination calculation, but it's important, and it shows us in wire bonding we need a very high yield per individual bond. Okay, now wire bonding, how does it work? As I have shown you, the ball bond first, I will address that first. So ball bonding is a process where we have on one side the so-called nail head bond. That's clear. That looks like the head of a nail. Yeah. So it's a nail is produced. We have a wire. The wire is taken and it is, let's say, boxed flat, and that forms the nail head. And how do we do it in wire bonding? We must imagine that is a bonding wire 25 micrometers thin, and it is in a capillary. When you look at that capillary, you could say it's very similar to a ball pen, where the writing element looks out of the body. Yeah, so it looks like that, and then we must form a ball. In former times, they used a small hydrogen flame to flame it off. So that's still the name, flame off. But that cannot control the size of the ball well. Good method is you have a capacitor and you discharge it against the end of the wire. And when you know the voltage of the capacitor, you precisely know the energy. And when you know the energy, you know which volume can melt. Yeah. So just by the charging voltage of that flame off capacitor, you determine the size of the ball. I like physics, I must say. And in that way, a ball is formed, and then the ball is just pressed onto the part, and the part is in almost all cases the chip. The reason is a chip doesn't like local stress. So if a chip gets local stress, it will crack, or it will have so-called cratering. That is maybe a crack going under the wire bond. but still the wire bond can be is not completely detached from the silicon, and in that way you have some risk device because it has a defect, but it still works. So in that way, doing the nail head first, and you do not overload the chip, and you get a electrical contact. Then the capillary is moved up and it is moved sideways, and we form a loop here. And then the edge of the capillary is used to press the wire on the second bonding side, and then the tail is pulled. In former times, it was just ripped off, but that has an advantage and a disadvantage. The advantage is when you rip off the wire and the bond, when it comes off, you say, okay, it was not strong enough. On the other hand, even if it survives, you could do some damage to that by that ripping. Therefore, presently, the process is in a way, the tool is kept in place, but the wire, or it is even pressed onto the bond, and the wire is pulled back and ripped off. In that way, yes, we have that tear off, and trying to avoid to damage that second bond here. And then we have a free tail of the wire, and then the whole game starts new. And in that way, we can have a high rate. Highest rates of bonding are, you could say it's like a sewing machine. You cannot even see the movement directly. The number of loops we can have, it can be up to, let's say, 10 to 20 loops per second in the high performance machines. And yes, here we can also see such, that also was by Tanaka, a bonding wire, that's internal structure. So we have a large grain structure where the wire was molten. We have the grain structure of the gold in areas where the wire was produced by wire drawing. And also in the neck region here, we have a recrystallization. So we have larger grains, and that is something we do not really like, because larger grains are always weaker than finer grains. And therefore, the Tanaka, they just did that in order to show how the internal structure is. Of course, you can make a microsection to look inside. Here they did, I think they used a so-called focused ion beam. So you shoot gallium ions on the surface, and the etch rate of grain boundaries is higher than the etch rate of a grain. And in that way, we can see the grain boundaries. And as we know, every of these grains is a single crystal of gold. Okay, here is such a loop that was from another project with Micronas company. We can see here that is a stamped lead frame. Here we see that from the stamping edge here. Here is a second bond we have. And here we can see the adhesive goes directly under the corner of the chip. In order, let's say, for the sake of Tanaka, their image they did, which I initially showed, that was specially made, and the assembly was specially made. So they should have tried out how to glue good. Here, the Micronas companies, they produce millions per month of these devices. So of course, they have their gluing process much better under control than when you just do a single demonstrator. Yeah, so that's also clear. Yeah, the other process of bonding is ultrasonic bonding. Here we have the wire end, and the tool is not a capillary, but it's typically it's a hard metal tool, and that has a hole, and here is a bond foot, and the wire comes through the end of that tool under the foot of the bond. Then the whole thing is pressed by that wedge onto the substrate by pressure, temperature, and ultrasonic movement. The bond is achieved. Then the tool takes off. Again, a loop is formed to the second bond. And the second bond is formed. Again, here we can see the tool is kept on the bonding side. The wire is pulled back. That location is always weaker than the wire itself, so it works. And then again, the machine must feed in the tail, so it comes under the bond foot here, and then the whole game starts again. So that's another process. That is so-called wedge bonding. The other with the nail head is the so-called ball bonding. It's also called nail head bonding, and that here is wedge bonding. Wedge bonding is most important in power electronics. For instance, that is done was done in one of our projects. Here we can see that was a project on adhesive bonding, so from one of my PhD students. And here it is a so-called heavy wire, which has 0.3 millimeters. What we can do with wedge bonding is so-called stitching. So it's like a sewing machine, you could say. You do the first bond, you go the loop, you go here, for instance, that's a diode. You do several stitches on the diode. The advantage is then you can distribute the current better on the diode. Then you just do it with the metallization alone. After the here 1, 2, 3, then the fourth is again on the transistor here, and again we make a loop on the transistor. So we have seen we had 5 bonds in a series. That here is the gate bond. It's not necessarily a thick wire, but if we are already on the machine, we use that, of course. A disadvantage of wedge bonding is that you can only have very small angular variations. With ball bonding, from the first bond, because it's symmetric, you can go in every direction. Yeah, the whole system is symmetric. That's not the case here. The initial direction of your wire must be kept. You have small variations because the diodes are more apart than, let's say, the size of the chip. So it works a little, but not too much, because otherwise you would have too strong deformations here. But that's a good example of heavy wire bonding. And the rest we will see next Friday. Okay, thanks for your attention.